Welcome to Gabversity, once again, where facts don't care about your feelings at all. And what I have to say is that there is this beep in the bus that is gin and tonic that is beeping every Hey, Amy Loren, long time, welcome back everybody. It is beeping like mad every about 50 seconds and it is pissing me off. I feel like I want to grab it and break it. It is driving me crazy. Anyway, I will try to get through this physics. James Joseph, everyone may. I feel like, hello, my dear, welcome back. Yes, you can probably know the feeling, right? So this is our winter tan, as I love to keep saying, and Gabversity, where facts care not about your feelings. Let us begin. So here we are, our friends. Here is the question that your scope about enclavism was a revelation to me. Thank you. Oh, wow. Hey, James Joseph. Welcome to everybody. Lovely to see you. I'm glad. It's so funny, like, stuff that I share that I think is just, everyone seems to know it. I keep forgetting that, my life as an autist means I don't spend much time with people, and I spend a huge amount of time with, just with maths and physics. Thank you. So that really means a lot. I love that. So, everyone out is doing their thing. Hey, the Dome Father's in. Everyone's in. I have to say, there are some people like the Dome Father and Amy Loren. They are like nuclear weapons. They come in and they bring I think the last one I had Dome Father and Amy Loren, and we had 1,600 followers. Italy and Europe. Boom! Yeah. So just before we start on our physics, we got to talk about enclavism versus multiculturalism. And the devil is in the wording, right? People, what the fake left does, man, anytime. I can weaponize the West. I don't care which proclivity you are a part of, whether you're left, right, straight, gay, whatever. But, yeah, absolutely. What the devil does is redefine. So if you have a question about enclavism, what they say to you is that, oh, so you're against multiculturalism, are you? So that is a deliberate, malicious swapping of a meaning whilst keeping the word the same. That is disgusting and deceitful and deceptive on multiple levels. And I find that horrific. And I'm a progressive, but I support free speech. As you guys know, those who know me, right? I'm a mad-ass progressive, but I will never, ever, ever force my opinion on anybody. I will sit and talk with you for like a month, and we will try to arrive at a conclusion. But if you and I don't agree, we don't agree. But I swear to you, the second I try and force you, that means that now you can force me. Sometimes. Sometimes. So that's the thing. So when people talk about multiculturalism, I say to you, go to Gabsmacked on YouTube and have a listen to my... It's on YouTube now. It's enclavism versus multiculturalism. And what happens is no normal, decent human being on any side of the aisle is against immigrants. That is the dumbest thing in the world. Look at me, I'm like an immigrant twice, right? I went back to the Middle East and came to Australia and back again, and I speak all these languages, and I'm a mad-ass progressive, and yet all of you are awesome, and you're a liberal. There you go. Alrighty? So the point is, I barely meet, like less than 1% of 1% exactly. Hamiltonian operator, and voila. Yeah, I like this guy. All right. Absolutely. So anyway, if you want, go have a look at enclavism versus multiculturalism on YouTube at Gabsmacked, and you'll see what I'm talking about. Anyway, I don't want to bring politics into Gabversity any more than we have to. So let us move into solving your scope's awesome fair guy. Likewise, my friend, you are Mr. Charisma with a tan. That's how I remember you. All right, James Joseph. Alrighty, so here's the question. You're going to need to know a lot of maths and calculus. If you don't, then you can just watch along. All right, here we are given a snapshot of a wave, right? The snapshot of a wave at time equals 0 happens to be this. So nice, I need one. Alrighty, official MPR, welcome back. Here we have a constant outside, which you could sort of call the amplitude if you want to. And here we have the quantum wave function representing a movement of a particle. Stupid. This is one of the problems with Periscope. It's this focusing thing. Right, come back, my friend. You can do it. Yeah, exactly. He knows his stuff. All right. We're waiting for it to come back. 10, 9, 8, 7, 6, 5. All right, it's not coming back. It's not coming back, so I'll talk to you. All right. What we have is we have a snapshot of a skipping rope, right? The skipping rope is where all the particles can exist at that time equals 0. So it's a photo. So it's a one-dimensional possible movement of this particle. And what it's saying is that it is made up. Try using zoom instead of moving it closer. All right. See, this is why you are the Loren. Don't mess with the Loren, my friends. All right. So let's try it. I'm going to try Amy Loren's advice. White is your problem. Zoom in, biatch. You can do it. No, doesn't want to do it. He's just a stubborn mother. If I put my hand in here, it might work. There we go. All right. So here it is. Now tap screen. Thank you. So this is the wave function at energy level 1. Am I looking at the right problem? That's 2.6. I wanted 2.5. Sorry, right here. All right. So that's psi 1. Thank you very much. I have a good teacher. That is the energy level of the particle, the quantum particle, the lowest energy level. Here is the second energy level. And what they're saying is that this total particle, we've taken out time, and it's one dimension of space. It's the pen that it keeps... All right, I'm taking the pen out. Put my finger back. All right. So now that is made up of these two waves. These are two different waves. And when you add them together with this amplitude, you get this wave. What they're trying to say... Taylor series is bad boy. Yeah. All right. My friend, you need to wait for like 10 lectures from now, and then you can just join in. You don't even need this lecture. All right. So, finger is same for focus. It seems to work when I put my finger there. Oh, that's a bad, dirty joke. Let's not focus on that. Alrighty. So what we're trying to do, we've got to figure out what is the A, and then we're going to figure out the other waves. Right? So how do we do that? First of all, we're going to normalize the function, as I've told you in the last lectures. Okay, so here is the normalizing of the function. What we've done is we've taken that, and we know that that equals 1, right? But it also equals a squared outside the integral of this wave, right, multiplied by the wave by itself. Okay, the wave by itself, but it's the modulus, right? The modulus means that you can use the complex version of the wave, which is the alternate dimension of the wave, and the actual wave itself. And together that makes the modulus. Now, why do I do it this way? Try using sketch to point. I don't know what sketch means. How do I use sketch? You mean like this, right? So the point is on that is that we want to square the wave function, right? Because when we square it and normalize it and integrate it across the location, all the potential locations of the particle, we get 1. But it also gives us that wave. And you know, the wave was made up of two small waves, so we can square the whole thing. Well, what's the point in doing that? There is a point. The point is, by doing that, is that we can eliminate certain variables to leave what's left. And that way we can find out what amplitude is, right? That's the whole point. Okay, so here we go again. What we've done is we can square this, all right, my friends? We can tap the 3 dots on the bottom of the screen, and then it's focused again. That's crazy. So the 3 dots automatically focuses. Sketch, it doesn't say sketch anywhere though. I don't know what sketch is. Oh, and then do this. So what you're saying? This is weird, man. This is like a lesson for me in Periscope and a lesson for you guys. All right. So remember, right, from our last lectures, that when you square this, right, you square the modulus of this, you get 1 and integrate it. So we're going to do the same thing for both sides. We're going to integrate this and square it. And we're going to, by doing that, right, look what we get. We get this, right? This Right? Oh, it's done it again. No. Maybe draw. Scroll down in dots. There's nothing. All I have is broadcast details, ask to follow, ask to share, share broadcast, hide chat. That's all I have. Find sketch. I don't have sketch anywhere. Unless it's on this one. No, it's not here. I got broadcast, ask to follow, ask to share, share broadcast, chat, and I can't scroll anywhere. I don't know what's going on. I don't know what I'm doing. Alrighty. I know he's so great sometimes. Alrighty. What I'm going to do is just write. Because when I write, right, it seems to be alright. So, such a trooper. Sometimes, my friends. Sometimes we can troop. Alrighty. So. Sorry, we're losing people. We're bleeding followers. Alright, have a look at this. If we get A plus B, right, squared, that... Ah, you piece of shit! Swipe down to stop, double tap the flip camera. Alright, A plus B, that's alright. A plus B all squared, right, this is basic mathematics, equals A squared plus 2AB plus B squared. Alright, so that's not a bad strategy. The problem is we're stuck with this 2AB in the middle. Sorry Gab, sketch is there. I don't know why it's not there for me. I'm scrolling and scrolling, I'm getting nothing. Unless I go to broadcast details. Nothing. Maybe I have to update Periscope or something. I'll try and update it. Alright? But here's something interesting. What we want, we don't want this, we want this. We want the normalization and square. Okay? Now that all squared is different because that is the same as doing this. A plus B, okay? A star plus B star and normalize. Now this is just a mathematical trick because that, right? That equals, right? Finger gloves, yeah. I cut them with scissors. All right, that equals A star plus, right? A B star plus B A star plus B star. All right, why is that important? Well, it's important because in physics, this wave at level 1 and this wave at level 2 are orthogonal, right? They are orthogonal. What does that mean? Orthogonal is like if this is north, imagine this is north and that's south, and that is west and that's east, okay? All right. Look at this, east is orthogonal to north. That means it doesn't matter how far you go east, you can never go north. You can go east for infinity, you will never go north. If you went east-north, then over time, you could get north, right? But if you only go east, you will never get north. And it's the same with these two ways. These ways are related like north and east. They are orthogonal. So you can never get this from this. And what's interesting about this is that mathematicians discovered a really cool secret. And the secret is this. When you multiply the conjugate, which is the mirror image in an alternate dimension of this, by this, you get 0. And that means that this equals 0 and this equals 0. Star implies the conjugate. Sorry, so I'll show you what it means. So here, right, this is I, this is real. All right, this is the real number line, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the second dimension line. What's interesting is that if you have a number here, which is like 1 plus I, right, that this component is in our dimension. This component is in a parallel universe. What happens is that there is another parallel universe that goes this way, which is 1 minus I. And when you multiply that by that, they are orthogonal, right? Yes, they are orthogonal, exactly. These ones here, when you multiply them by each other, you get 1, right? So that's really interesting. In this case, right, what we're doing is we are multiplying this, right? This one has an orthogonal component here, right? This orthogonal component is in another dimension as well, and that's orthogonal to this. And mathematically, when you multiply this by this, you get 0 every time. And what that means is that here, this one and this one, so basically this is in an alternate universe. If this was in our universe, then that by that would be 1 because they're orthogonal to each other. But in the alternate universe, perpendicular and orthogonal, nothing. Orthogonal and perpendicular are the same. With one difference. Perpendicular and orthogonal are the same in our universe. But in other universes, and on the micro level and in string theory, orthogonal does not have to be perpendicular. There are different types of dimensions, but in our main universe, perpendicular and orthogonal are the same. Yeah. All right. So what happens is that this is perpendicular to the mirror image of this, but when you multiply that with that, you get 0. Right? Mathematicians discovered this, and this is just a mathematical trick, which is what we've done is we've converted this, which was that, which was that, which was that. We converted it using mathematics into this, which equals A star plus B star. Now what's awesome about this, right, is that that equals the modulus of A, right, plus B, modulus. Modulus is like absolute value, which is the real value, right? So the modulus of this number is actually here, right? It's on the real line, and the modulus of this number is also on the real line, right? Because basically, you guys call it absolute value, but really what absolute value is, it's a subset of modulus, and a modulus brings numbers from other dimensions into our dimension. So the shadow that a number makes in our universe from other universes, the shadow is what we call the modulus, right? And it turns out that the modulus of 2 multiplied by its version in the other universe is the same as doing 2 by 2. And it's just a mathematical trick. And by doing that, we get this, which means we get this. Sorry, the squared goes outside. Well, who gives a shit? Why is this important? This is important because look at this. Look at this, my friends. The modulus, when you integrate the modulus of the wave squared dx, you get 1. The modulus always equals 1 when you integrate it. Integral of the modulus of the wave function squared dx equals 1. And that is brilliant, because what that means is that we've been able to convert this into that, and that equals 1, right? That is the genius of it. So by doing that, right, we have been able to do this. We have been able to say, since that is orthogonal to that, then that is that. Therefore, 1 and 1 by a squared. That means a squared 1 plus 1 happens to equal that, which equals 1. And so therefore 1 equals 2a squared, you see, because that equals 1, right? So therefore a has to be 1 over root 2, QED. And there you go. So that, my friends, is how mathematicians design mathematics. They invent or discover mathematics. Anything over 4D equals orthogonal. Interesting. Mathematics is indistinguishable from logic when you get down to the abstract maths level. So, for example, thank you very much, Captain Deltron. Right? So what we have done is we discovered A from that wave, and that's brilliant because we have used pure logic, which is abstract mathematics. Abstract mathematics dives into pure logic and extracts from pure logic mathematical tools, and then physics use those tools. Your comments are so delayed. Oh, that's all right. It's me. I'm in Australia. It's got to come all the way over the Pacific, or the other way around the Atlantic and through the Middle East. You know, that can cause problems. Yeah. Awesome. Alrighty. So what is the point of what I was saying? The point is, yeah, we use we take from the mathematicians those tools that they invent, such as the orthogonality, right? Or, you know, these Hermitian matrices and all these type of things. Hey, Paraguay, encantado de conocerte, señor Rogerar. A bit of philosophical question would say, yeah. Yeah, so the question is maths, does maths already exist, or did we invent it? I mean, I've only done like 1 year's worth of abstract mathematics, but my understanding of abstract maths is that it is something you discovered, which is, roll them R's, which is something outside of our universe. It's something that's timeless. In fact, abstract mathematics can't be calculated unless you assume it's timeless, right? In fact, let me show you an example of some abstract maths, right? Here. What is a real number? What is a real number? What is a real number? What is it? Is half a real number? Sure. How about half of a half? Yep. How about half a half? Yep. So how do you even figure out? No, well, an integer is a subset of the real numbers. So you have integers, you have quotients, you have irrationals, you have real. Now, real are uncountable. Seem to break down at 10 to the... Mathematics doesn't, but physics does, yes. All right, so this is not a complete definition of the real number, but have a look at this. Right? Have a look at this. There is a number. Let's just call it x. There is some number x, mother effer. There we go. X, such that, right? Such that, right? X, right? And this is not a complete definition. You divide x by 2, right? And then you divide that by 2, and then you divide that by 2 for infinity. Okay? That is one of the real numbers. So you do this for infinity, right? You can call it an infinite series. So basically, I mean, I did not define it. Do not take this as abstract maths. I have not taught you an abstract math course yet. But basically, to define a real number, it involves infinity. Because one number that's a real number, right? It's basically an infinite sum of irrational numbers. It all comes down to 42. Right? But basically, a real number is an infinite sum of irrational numbers. Sorry, an infinite sum of quotients was what I meant to say, or irrational, yeah. So, you know, like for example, you know, how do you get the square root of 2? Well, it's an infinite sum of smaller and smaller numbers, and you will never ever get to the square root of 2. It's impossible, right? So it goes on for infinity. So these numbers can't exist unless you look at them from outside of time. And this is part of why I say the annoying thing. You can say whatever you like anytime, Amy. All right, so what we've just done is we've been able to figure out... Oh, we're getting sidetracked. I'm never going to finish. All right. So as I said, we just discovered... Oh, the beep. Yeah, I know. It's crazy. All right, so we have just discovered that A equals, as we said, 1 over root 2, which means that the wave, right? The wave, right? This is the full wave, xt, equals 1 over root 2, okay? Outside of phi 1 of x, which is the wave function at the first energy state, plus phi 2 of x. All right. So now we have been able to build this up, right? Oh, sorry, that's x at 0. Sorry, that's at 0. So this is a snapshot in time at 0. 1 over root 2 that. Okay. Now the next step that we want to do, right, is we want to convert this into the Schrodinger wave equation, right, and reconstruct time. Now we've done this before. All we have to do now, okay, is say, so therefore the wave equation at xt equals, and now we can build the whole bastard, right? What have I done? Sorry, excuse me for a moment. There we go. Okay. The wave equation, Gab, I'm strolling hospital corridors, just burst out laughing at some of your comments. That's good. You need some laughter in that place, you beast. I retweeted your thing. I called it, what a beast, the Dome Father. Alrighty. So, this here is going to be, right, build the bastard. Alright, root 2 over 2, right? Then the wave, okay, at the first energy state of x, and now we're going to add the time component, which is e to the minus I omega t, plus the second one, right? And the second one's at the second energy level, so that's going to be slightly different, which is root 2 over 2, okay? That over 2. Now the reason, see, that up there was 1 over 2. This is root 2 over 2, because when we build the wave function, we put a 2 on top. All right, but anyway, we'll get there. Where are we? Okay, so that x. Now remember, now we have e to the minus n squared, and n equals 2 because it's the second energy level, and n squared 2. 2 squared is 4, so minus 4 I omega t, right? Where omega, right, if you guys remember, equals, and of course I don't freaking remember, so I'm going to go back and show you, it is pi squared h bar, okay, pi squared h bar, and remember h bar is the pixel, but this is the reduced h bar, so this is a pixel in 1 dimension, so it actually doesn't even have a form, try to believe that, over 2 by the mass by a squared, and a is the distance that the particle's moving inside the box, okay, so that is up here, and that's the full wave function right here, and I'll show you what it means in a sec. Alright, what does that mean? That means that given the particle's location and given the time, we know this wave function, so we will know what the mass is. Or, if you know the mass and you know its distance, then you can find, using this equation, where the particle should be given a certain time. My dear, physics when you're drunk is the best, because then you don't have to worry. That's all good. My dear, it is all good. You can get philosophical and drunk, or you can get drunk without being philosophical, or you can get philosophic drunk, or you can get drunkosophical. Whichever one works for you, it is all good. Alrighty, so why is this important? Okay, where am I? Oh, I think I missed something. Alright, so now let's go to the next part of the question, which is, we need to find where am I here? Alright, so now let's move across. Where are we? I'll just be if no use of. No, don't be silly. If you guys find it boring, let me know. I'll just go and do this on my own. Don't be silly. Don't be shy, my friends. You guys make this channel. Without you, facts have no feelings to not care about. Alrighty. So now what we're going to do is we are going to find the wave function squared, and there's a reason for that. All right, let's do it. The wave function squared, right, it's just a bit of mathematics, so I'm not going to bore you with all that, but the wave function squared is going to come out to be, right, and this is the normalization. No. Right, wave function of xt, this is a two-dimensional wave. That's one dimension of space and one dimension of time. Don't be silly. All your company is always fun. You guide what's going on and ask any questions you like. All right, this is the normalized wave function squared equals a half, okay, 1/2, outside of the smaller waves added up, which is, we've got the wave representation of the particle at the lowest energy state squared, plus the wave representation of the particle at the second lowest state squared, plus 2 multiplied by the wave function at the bottom state and the wave function at the second state, okay, cos of 3 omega t. Now, why is this important? So this is just a mathematical representation. All we did, we just squared this Schrodinger equation in Periscope. All right, well, welcome from Paraguay, Rogerar. Benvenidos a la Schrodinger ecuaciones in Periscopes. Alrighty. Why is this important? This is important because, right, the integral of this equals 1, which means that we can figure out what all these are, which is so important. Okay? And now we want to find the average position. So the average position is what we call x, like that, x average. And all it is the integral of this, right? It's like this, equals, oh, I'm going to sneeze, excuse me. Oh, sorry. Oh, sorry about that. I'm sneezing like crazy in this bus. I have bus allergies, also called busagies. All right. Yeah. Bus not funny. If anyone got that joke, that involves snot and funny. All right. Here, it's going to equal, hello, help me. Are you drunk too? To answer your question about being drunk, I fell into a vat of alcohol at the age of 11. And so I'm always drunk. If full matter teleportation were possible, does that also mean that time travel will be possible as well? Time travel is definitely possible. In fact, it happens all the time. Satellites that orbit us at geostationary orbits, in other words, they're locked, like, you know, for drunk Gab smack table, damn straight, my friends. This is the autism. I think the autism keeps you as a child and just keeps you not giving a shit about stuff. Yeah, geostationary orbits, so the ones that are locked on the US for your phones, they travel, we travel into their future all the time. Teleportation is an interesting one. Thank you. Gesundheit. Teleportation is interesting because even though you are could be teleported, your particles are different. So who is it really that comes out onto the other side? Then back out. Well, yeah, like if you teleported to the other side of the universe, then you would be going into Earth's past, right? You could look back at Earth and you'd be seeing it from, like, you know, 1 billion years ago or something like that, if possible. But, you know. All right, gin and tonics. See you soon, my friend. Average position. Awesome. Teleported particles. We have. That's exactly right, Rob Collins. We have. And what happens is the first particle dies, and then a second one takes over. Acceleration without much mass. Not with teleportation. With teleportation, your particles are destroyed, and then new ones represent what you are on the other side, like a fax machine or email. All right, getting back to the average position, my friends. The average position, sometimes known as missionary, is also half of the integral from 0 to a of x outside the wave function. And this is the two-dimensional wave function. Later on, we're going to do four-dimensional wave functions, which will have all space directions plus time. That'll be 4 dimensions. But for now, we're just going to do 2 dimensions to make it easy. All right, and that, once we do all of the actual mathematics, I'm not going to do it in this course, that is going to equal a over 2 minus 16a over 9 pi squared, right, cos 3 omega t. All right, so what does that mean? That means that the average location of this particle will exist at a over 2, which is halfway, minus 16 by the distance divided by 9 pi squared, and the cosine of 3 by omega by time. And that there is a function, and that is exactly where you would expect to find the average particle, the average of the particle over time. Right, so you're going to get the particles all over the shop, but the average of those will end up at that location. Right, now why is that important? The particle's mean position oscillates about the midpoint of the world with an amplitude of about 0.18 a. You're very clever. I'd love to study this. Awesome, thank you. I would love for you to study this. That would be great. If you guys can assist, you go to Patreon. It's $1 a month, Patreon/Gabsmacked. And once I get 2,000 subscribers, I think I only have about 50 at the moment. We've got to get to 2,000. Once we get there, you also get the private videos, but then I can do heaps of courses. And at the moment, I'm in the bus, I'm at work. Time dilation. Yeah, I would love to teach you guys time dilation. Anyway, but you got to thank Amy Loren. Amy Loren, my dear, is the connection. Her and the Dome Father are heavyweights, but I love everyone. Alrighty. So, we've done the average position, and now we want the average momentum. So the average momentum, right, is, if you guys remember momentum, it's mass by velocity in classical mechanics. In quantum mechanics, the average momentum is also mass by velocity, which is mass multiplied by, and this is the illusion of velocity, which is d of the average of x dt. And that just happens to be 8 h bar over 3a, and the sine, which is trigonometric function of 3 omega t. I just got that. 120 pounds, oh my god, you are tiny. Jeez. What am I? I'm 85. So what's 85, 88, 160, 170, 180? I'm about 190 pounds, I think. Alrighty. So now we found the momentum, which is interesting. That means we know that the average momentum of this particle, based upon the average speed of the particle, viewed monitored. Yes, that is correct. I would refer you to, if you go to YouTube, there's it's called PBS, type in YouTube PBS space quantum mechanics, and there's a 16-minute video that came out last week that talks about how you can affect stuff in the past with special quantum particles, and they still don't know why it happens. It's quite fascinating. You're like 5'2". Oh wow, you're tiny. Jeez, you're like a foot shorter than me. But I heard in America, people are quite tall. In Australia, I'm normally the tallest guy in the room. I think in America, you guys are taller. Man, we should do a combined scope, Amy, where you sing and I'll play on the piano. Unfortunately, we can't swap because I can't sing. Fancy flock, here to watch some physics. Here is the question. The last question for this question. 5'4", hey. What is the chance that the energy packet of this wave function is going to be at the first energy level and not the second energy level? Well, here is the answer. Yeah, I mean, it is an illusion. We already know that we are computer software. Whether God made it or whether something else made it or whether infinite universe theory is correct or whether we are software programs, no one knows. But we now know to like at least 90% certainty that we are made up of codes of pixels, and just like computer games. But we feel real because when we touch someone else, hey, they are also made of the same stuff we are. So we feel real to each other. Hey. All right, so let us go into the Hamiltonian. The Hamiltonian, yeah, which is the combined energy, right? And we want the average Hamiltonian equals half, right, of E1 plus, it's amazing how everyone knows everyone, 2. Right? Well, that's only because of the original equation. The original wave equation was this. If I can find it. Where is the original wave equation gone? Where's it gone? Oh, it's right here. The original wave equation is 1 over root 2 of that and that. So they are equal components, which means it could be E1 and it could be E2. So the energy from here, right? And there's an energy from here. All right? And they are equally contributing to the actual wave function, which means that the chance that it's E1, probability of E1, which is prob of E1 equals 50%. That's it. We're done. Next question. Next question. I have the energy to go all night, my friends, and that is not a dirty joke. I need to take off my gloves and my jacket because it's getting really hot in here. So excuse me for a moment. While I take off my gloves and jacket, 25 people live, E equals mc squared or m equals... sort of. In classical mechanics, that's true. But in relativistic mechanics or relativistic physics, it's actually... Oh, whoops. It's actually epsilon mc squared. This is the real equation, by the way. This is just a side note. In relativistic mechanics, E, right, equals epsilon mc squared, where epsilon, sorry, that's E, it's not epsilon. Epsilon equals 1 over the square root of 1 minus beta squared, where beta squared equals v squared over c squared. Now, I don't know if that's actually true. I think it's... take off your gloves and jack it. What? Yeah, it's getting hot. So, c squared is the speed of light squared. V squared is the velocity that you're traveling. And b squared is your velocity relative to the speed of light. So have a look what happens here. That's awesome. Oh, you're being sarcastic, sorry. So if you're in a spaceship and you're traveling at the speed of light, look what happens. And this is why you can never travel at the speed of light. This is what happens. All right? If you're traveling at the speed of light, that means, that means that V equals 1, right? If V equals 1c, right? Which implies that V squared over C squared equals 1, because 1c squared over C squared equals 1. Okay? So if I chuck that into here, epsilon, so therefore epsilon will equal 1 over the square root of 1 minus 1, which equals 1 over 0. What? 1 over 0. Infinity? Infinity! So it doesn't work. In other words, you can never travel at the speed of light because you would need to have an infinite amount of force to push an infinite amount of mass. You would need undefined. Hey, my Roton, that's exactly right. Infinity and beyond. It's an approximation as long as you're traveling less than about 14% of the speed of light. Because this is what happens. I'll show you the graph. Energy equals mc squared. All right, so that's energy. Just become massless here, like light, exactly. mc squared sort of works like that. Okay. But when you have Tesla, that noise, I know. When you have, what do you call it, the Lorentz transformation, then this is what happens. You actually go like this, right? And so the approximation keeps going like that. So as you get faster than, ooh, I missed your last comment, I'm so sorry. As you get faster and faster and faster, that approximation of mc squared without the Lorentz transformation, which is epsilon, which is this, right? This might be slightly off, I forget the exact equation. Right? This starts to happen. You get this wrong business up here, and the error gets really, really, really big, right? So this is a bit, I don't think it's E actually here, but whatever, you know what I mean. It starts to deviate the more you go faster. The pen. Somebody bought these pens, which is great news. All right, let's go to the next question of quantum mechanics. The next comment, I'm going to rewind the comments and see that last question someone asked. Even warp bubbles. Yeah. Nope, don't know anyone. Pen or B. So what would time have to do with Schrodinger's cat theory? Well, the only thing that time has to do with it is that you need a location in time to take a snapshot of the cat in the box. It's good enough to go to the moon, not much else. That's exactly right. It's exactly right. If you want to, and heading to Mars, it's okay, sort of. But putting satellites in orbit doesn't work, because satellites, the difference, gravity slows down time, right? Yeah, now that you've told them, they'll notice it. I just want to punch it in the head. I want to go kick that beep. I don't know where it's coming from. I remember once someone stole the hammer, and he was the only guy in the bus, and as soon as he pulled the hammer, it goes, hammer removed, hammer removed, hammer removed, and it wouldn't stop. So then I went and looked at him, and he goes, I didn't touch it. And I look at it, the hammer's missing. There's no one else in the bus. I look at him, I'm like, are you fucking kidding me? He's like, I didn't touch it. And all I see is hammer removed. So for the next 3 hours, because I didn't have a bus, I had to drive for 3 hours. Hammer removed, hammer removed, hammer removed. I'm like, fuck you and your hammer, man. 3 hours. It was just the worst thing in the world. All right, let's do. All right. Yeah, I know. All right, let's do the next question. You never drop MC Hammer damn straight. All right, here we go. The next question, I'm going to show you another particle. And what's interesting is that I'm going to show you when a wave function's out of phase, you keep him in the bus. I kept him there for 10 minutes, and then I call up the boss, and the boss is like, oh, you know, you got to finish your route, you got to be on time. Never know when you need a parachute, yeah. Parachute removed. Yeah, that would be really scary. All right, what I'm going to show you now is that the last wave I showed you was like two skipping ropes on top of each other, which made a bigger skipping rope. Now I'm going to push the skipping ropes out of whack, and it's going to completely change the particle. And I'm going to show you mathematically what that is. Yes, that's exactly right. All right, so here we go. This here is the wave function x0, which is frozen in time, equals, so A, similar like before, all right, and we still have the first energy level, okay, plus we still have the second energy level, just like before, all right, but here is one difference. We are shifting it out of phase, EI theta, which all that means is that the two skipping ropes are on top of each other. Now we took the top skipping rope and we pushed it a bit to the right, a little bit, right? We made it more conservative. All right, so now we're going to do the same thing as before, and we're going to find a slightly different answer, which means that the quantum particle has a completely different location, right? It's going to completely throw it out of whack. So you ready? Let us turn the page and I will show you what happens. So now the wave equation completely changes and it becomes this. Right? Now we did all of the same work, right, as before, and we're going to get this. Right, that's the two-dimensional equation, which has time, and we're still going to get root 2 over 2, just like before, and we're still going to get psi 1 of x e to the minus I omega t, so that's still the same, plus here's the shift, plus psi of 2, right, psi 2 of x, so that's the second energy level because you couldn't touch this. All right, e to the I theta minus 4 omega t. All right, so what's happened is, maths is artistic, absolutely. We have a theta shift, all right, and that just means that the equation, this part of the equation, has shifted slightly. Okay. Now we're still going to find out the average position of x. Hammer time. All right. Have a look what happens. What happens is this: the average position is now missionary pushed a little bit to the right. Right? X. Excuse me, I'm going to use the other end of this pen. This job is pretty cool. I get paid to sit in the bus here just in case there's an emergency. Most of the time, I just sit here after picking up the... I love the comments. The comments are better than the class sometimes. Oh, man. All right. The average position, hey, is A over 2 minus... Sign up to Patreon, and we're gonna, once we get to 2,000 members a month, I'm gonna do all of the basic maths for you guys and teach you all the way up. I'll even give you tests to all of my members. To my members, you'll get tests and I'll grade you on them too. No problem. And we'll start right from 1 plus 1 all the way up to this. Over 9 pi squared. What type of bus? It is just those large 80 passenger buses. Alright, cos theta minus 3 omega t. So the average position has shifted. Yeah. What's the... The name of the driver is annoyed. Alrighty, so there you go. So in other words, the amplitude of the wave does not change, it just shifts it across left and right. So now let's look at the next question, which is 2.7. 2.7 Alright, let's have a look at this wave function. Here's a new one. This one here is xt. If we get below 15 people, I'm going to stop. I'll just do it myself. Sorry, x0. I only went to pre-calculus. x0 equals, where am I? We have two states here. This is interesting. We have ax. We should sell these pages. 0 less than x less than a on 2, right? 0 less than equal to x less than equal to a over 2. Alright, so that's on the left side of this well, and on the other side it is a minus x for a over 2 is less than equal to x less than equal to a. So what's going on here? This wave function is sort of, here is the well, right? And what we're saying is that is 0, here is x, here is a, and this part here is a over 2, right? So here is the particle, and it's just going backwards and forwards, you know, like a ping pong. Ping pong, ping 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 pong, ping pong pong, right? It's going backwards and forwards, and that mathematics just explains that, right? And it's represented by this graph. Here is the wave, and here is x over here. And what happens is that when it's 0, it's ax all the way to a over 2. So when we reach a over 2, right, the maximum is what? Is a over 2. It would be, let me think about this one. Where am I? I don't want to leave you and you stop. Oh, well, that's okay, my good friend. You can certainly go if need be. Don't be shy. What am I doing here? Am I doing even the right question? Yeah. And determine the constant a. That's exactly what we're doing. Alrighty, so we're going to say that at a over 2, let's put a over 2. If we put a over 2 into here, it's going to be a by a over 2. Ping pong, pong pong. Exactly. So a by a over 2 is the maximum, and a of x is the graph. So this is high school maths here. This is ax, which means that as x gets bigger, you times it by a, right? But look, as x is a on 2, you just put a on 2 into x. That's a times a on 2. That's it. And that's where it is, and that's the graph ax. Right? Now this one is AA minus AX, which means it's going to go backwards. So when it's A on 2, that's going to be the same. 42. 69, dude. Alrighty. So we know that the average location of the particle is going to be A over 2. And we want to determine A. Well, that's going to be easy. Remember that the integral from 0 to a over 2 of ax squared dx, huge time lag, yeah, there is, yeah, plus the integral of a over 2 to a of a minus x dx, all of that equals 1. And that's the original formula, which comes from here, the integral from the beginning to the end of the tunnel or the well of the wave function modulus squared dx equals 1. India. So here you go, and that equals 1, and all we have to do is integrate these. All right, so if we integrate these, we will get, let's start integrating the new position name. A squared. Now the integral of this is going to be ax cubed over 3, hammer removed, which is a over 3x cubed from 0 to a over 2 plus a squared. And what we're doing, just so you know what we're doing, calculus, we're finding the area under this curve. So that's the integral from 0 to a over 2, and then that's the integral from a over 2 to a. And that's what we're doing here. That's the area under the left part of the triangle, area under the other side of the triangle. That's all we're doing. Particle horizon versus Big Bang. 17. Oh, we're getting close. I'll probably hang up soon. All right. 16. Oh. 15. All right, we're going. Oh, 16. We're back up again. No, we're not going. Alrighty. And the integral of this is going to be, well, the integral of a is just a. Actually, I've stuffed this up. I've actually stuffed this up. What have I? That's. I've made a mistake. Freaking hell. And that's squared. Damn you. I call this the sideways hammer. Alright, so that is going to be... come back and focus. There we go. Alright, that's going to be a squared x, and then we've got minus 2ax minus 2ax, which will be minus ax squared, which will be minus ax squared. I'm sorry, I'm doing all of this stuff in my head. It's a bit tricky. And then plus x cubed over 3, a over 2 to a, and then we simplify that, which implies that a squared over 3, a squared over 3, come on bastard, come back. Alright, a squared over 3, I bet you I've made a mistake somewhere. And then, what's 2 cubed? 8 times a cubed over 8 xxx squirt show. Well, at least you looked. Alrighty. And then the next one is, this is a tricky bastard, a squared a cubed. Is this calculus? It is. Almost infinite. A squared a cubed minus a cubed plus a cubed over 3, and then that minus, this is a pain up the asshole, a squared a cubed over 2 minus a cubed over 8 plus a cubed over 24. Damn, man. That was a bit of a workout. I'm trying. Alright, so that means, and that equals 1. All of this equals 1. So that implies Shit, we're back up to 25 again. What the hell? This is a crazy. We're maybe I'm wasting time. You guys are terrible. All right, so this should be a squared a cubed over 24, which is a squared a cubed over 3 times 8 is 24. I guarantee I've made a mistake. Yeah, plus... Ah, jeez. A cubed. It is a pleasure. You're here for the math. Beautiful. Now I'm insulted. I'm like, I'm either don't deserve the compliment or get the insult. No, it's a pleasure to have you all for whatever reason. All of you. It's all about you guys, honestly. What am I? I'm just the method of facilitating you guys interacting with each other. Right? A squared minus a minus a third. A squared minus a minus 1 over 3. Crap, man. Minus. And then, oh, jeez. I don't know what I'm doing anymore. Minus, and then open brackets again. In relation to light speed. You know, what's funny is that it'll probably be around 26,000 kilometers or 17,000 miles because of the distance it has to travel to come over to Australia, up to the satellite and back. We had to do that for like first year physics. That's a very good question, actually. A squared over 2 minus a over 8. A squared over 2 minus a over 8. This is too much. Plus 1 over 24. Alright, it's getting too much. Life is good. Whatever. Find psi of xt. I can't be bothered anymore. Alright, next question. I just find the next freaking question. Alright, the next question. We're not even halfway through the questions. Freaking hell. This is going to take us longer than the damn lag. I could fly to the US and back. I have to do it though. I have to do it. I said I'd do it. I'm going to do it. So. Nah, stuff it. Can't be bothered. Let's look at another question. Let's do some integral calculus. Who wants to learn integral calculus? Can't be bothered. No, I can be bothered. Yay, okay. So, let's start with... Let's go. Alright. Y equals x. What does that look like? It looks like this. This line is y equals x. Here is 0, here is 4. What we want to do is find the area under this triangle, right? Now the area, let's do philosophy. Yeah, let's do philosophy. Let's debate climate change. All right, so this here is 4, and this is going to be 4 because y equals x. So that's 16 and half of that's 8. So therefore the area equals 8. Now that's one way to do it. Now let's do it via integration. The integral from 0 to 4 of x dx, right, equals, right, now this is x to the 1. So now we're going to add a power to that and then divide it by that power, 22 over 7, that's pi. All right, so what's 1 plus 1 is 2, x squared, and we divide by the new one, which is x squared on 2, from 0 to 4, right? And so that is the same as saying 4 squared over 2 minus 0 squared over 2. because it's from 0 to 4. So we put 4 in there, and then we take away when we put 0 in there. And what does that equal? 4 squared is 16 over 2 is 8. Minus nothing equals 8. And look, it's the same answer. 8, 8. There you go. So that is basic integral calculus. And I have to go blow my nose. I'm really sorry. So I have to go because I really have to do these things, and you guys are too much fun. We're getting distracted. But I think we have a new record, 1,009 viewers. Now the record was 1,700 last time. So now we're up to 1,009. And I'm telling you what, it's always when Amy Loren and the Dome Father come on at the same time, our viewership goes through the roof. So it goes to show you that little 120-pound Amy Loren, March 14, 2016. March 14, 2016. What's that about? This is all in decimal. I wonder if there is a numeric system where integration is easier. That's a good question. Not really. No, there are some National Pi Day. Oh, geez. 1413. Should have figured that out. Hey, Karen AZ, welcome back. Did you have a conversation with your husband about how physical affection is important? That's why you're here. It's all, I'm telling you now, the Dome Father and the Loren together make the Father Loren. And Father Loren is a weapon on Periscope. Oh, did it work? Or are you divorced? I think what I'm going to do now is, can you see me? This unconventional. Are you teaching math on Periscope? I am teaching math on Periscope. I'm teaching math on Periscope. But I really have to go. If I had 2,000 Patreon subscribers, then I could stay. But welcome, my friends. Welcome. Once I get 2,000 Patreon subscribers, then I'm going to do a whole calculus course from 1 + 1 all the way to multivariate integration. Periscope lag c² minus m minus 1 cx. Thank you guys. Don't apologize to me. Are you kidding? You guys are that's insane. That's like followed. Damn straight. Welcome, my friend. Oh, there you go. I just have to work on accepting scheduled time. Doesn't feel natural. It doesn't feel natural. That's correct. But you have an autistic husband, so you got to make that natural. But over time, when you get used to it, it'll actually work as well, because him being autistic, he's going to have some advantages as well, right? So, he's direct. You know he's not going to stuff with you. Like, he's straight up. You'll probably get all of that as well. So you say to him, look, I need it. Missionary position 4 times a week. No, but seriously, like, I need to go to dinner, and I need for you to put your hand on my hand for at least 180 minutes 6 times a week. You got to tell him that and say, please put it in your calendar, and please make it a repeated schedule, and every second week delay it by an hour so that it changes predictability, so you don't get bored of it. That's exactly right. Universal waveform function help. Not sure. What are we up to now? This is ridiculous. 1,023 people. This is insane. All right, guys, make sure I'm going to send you, will watch replay have to go, ask to follow. There you go. We'll get all you guys to follow. I hate being touched. Gab, go, P. What's my background? My background is autistic savant, mathematician, classical pianist, linguist, quantum physicist. Absolute pleasure. Welcome aboard to everybody. I'm going to get cracking so I can finish these equations tonight. I have to finish them tonight. No, sorry. I have to go complete these problems. Because I'm not getting them done with you guys. You're too much fun. But one of my scopes coming up is about climate change. That's going to be an awesome scope. I can't wait for that one. It's going to be a big one. Alrighty, I'll be flooding in a lecture from a professor. He's an American professor who is absolutely convinced that climate change is 100% real, right? And I'm convinced that it's some percentage contributed by humans. Whether it's 90%, 50%, we don't know. But we're going to get to the bottom of it on Gabversity, because facts give a shit not about your feelings. And if your feelings get in the way, tell them to go fact yourself. That's right. Night, night. From Sanford. The secrets will come up. And we've also got the astrophysics lecture coming up. All right, all the best. Lovely to see all of you. Gabversity, where facts don't care about your feelings. See you all soon.